Okay, so in this video we want to bring together everything that we've looked at over the last few videos in terms of introducing the normal distribution and how to use our CAS to find normal probabilities and other quantities around the normal distribution. And so this is our final video on the normal distribution, and hence in 2020 this is our final video for the year. So this brings to a conclusion all of the new content. At this point we can then get on to some revision. So this is a really exciting moment. I've just had an email from a colleague confirming that the exams are 9 weeks from today, so plenty of time to still be preparing and getting ready for those exams, but certainly time to be knuckling down. 2/3 of your assessment is in the examinations, and so therefore a significant opportunity still to impact your result in this subject. Right, so before we get to focusing on that, let's get focusing on finishing the course by solving some problems using the normal distribution. Okay, so we're just going to work through a series of examples here. I want to focus on the setting up. I'm going to refer to a document that I've published in the back of your notes, just in terms of, in particular, what you need to write down. I'll come to that at the end just to summarize. So, as I've mentioned in the last videos, if there's no variable defined in the question, you need to make sure that you define a variable. Okay, what does the variable actually represent? And then we need to define how that variable is distributed, and then we need to answer the question that's being asked. Okay, so examination marks in physics are normally distributed with a mean of 70 and a standard deviation of 9. If 11% of the students are given a grade of A, find the lowest possible mark for an A grade. Okay, so let's say P is equal to the physics mark. We haven't been given any sense of the units of those marks, but if there are units for your continuous random variable, you want to define them. And we know that P is a normally distributed variable. Its mean is 70 and its standard deviation is 9, but remember this notation involves variance, so we write 9 squared. Right, let's write down what we know. So 11% of students are given a grade of A. Find the lowest possible mark for an A grade. Okay, so we know the probability that the physics mark is bigger than or equal to A is going to be 11%, so 0.11. So essentially what we've got here, again thinking about what's going on, you know the mean is 70, you know the standard deviation is 9, you know that the top 11% of students get an A grade. Okay? And so therefore you want to know what is this grade above which they'll earn an A. Okay? So this is going to be an inverse normal probability, but remember inverse normal requires that we use the cumulative probability from the left, so we're going to need to use the fact that this is going to be 0.89. So we know therefore that the probability that the physics grade is less than A is going to be 0.89. So menu 553 for inverse normal. The area is 0.89. The mean is 70 and the standard deviation is 9. And we want to give, should really give it accuracy, find the lowest possible mark, so nearest whole number. Let's assume you can't get half marks. So therefore A is approximately equal to 81 marks. Okay, so therefore the lowest mark for an A is 81. Now technically speaking, it actually, it doesn't round quite right. Technically speaking, slightly more than 11% would get a score of 81 and above, but in terms of accuracy, let's just have a quick look. Menu 552, so if we did lower bound was 81 and upper bound was infinity, oops, not pi, mean of 70 and a standard deviation of 7, standard deviation is 9. We see that it is 11.1% get an 81 or above. But for the purposes of the question, especially if it says I've added, but round to the nearest whole number, you can just round to the nearest whole number. Okay, example 2. If the weights of students are normally distributed with a mean of 49 kilograms, so let's assume primary age children, and a standard deviation of 4 kilograms, find the probability, correct to 4 decimal places, that a student will be heavier than 53 kilograms given that he is heavier than 50 kilograms. Okay, so let's define a variable first. So W equals the weights of the students in kilograms. So if there's units, include the units in your definition. It can help you to be consistent through the problem. W is a normally distributed variable. The mean is 49 and the standard deviation is 4, so the variance is 4 squared. Find the probability correct to 4 decimal places that a student will be heavier than 53 kilograms given that he is heavier than 50 kilograms. So we want the probability that the weight is more than 53 given that the weight is more than 50. Okay, so we need to think about the intersection of those two things. What is it for something to be both bigger than 53 and bigger than 50 over the second thing? So something has to be both bigger than 53 and bigger than 50. It just has to be bigger than 53. Okay, so let's work out these two probabilities. So menu 552, normal CDF. Lower bound is 53 up to infinity. Mean is 49, standard deviation is 4. So that is 0.1587 on the numerator over weight's bigger than 50. So I'm just going to edit my previous line and make it the lower bound 50 rather than 53. It's a bit quicker than going through the menu, 0.4013. And so therefore dividing those two values nice and precisely with my CAS. Don't use rounded numbers to work out a new rounded number. So to 4 decimal places, we've got 0.3954 is the probability that a given student weighs more than 53 kilograms, given that we know he weighs more than 50 kilograms. Okay, example 3. Right, the amount of cereal in boxes packed by a particular machine is normally distributed with a mean of mu grams, so an unknown mean, and a standard deviation of 5 grams. If the advertised weight of a box is 500 grams, find the proportion of boxes that will be underweight. So therefore the proportion of boxes that actually weigh less than 500 grams, even though the advertised weight is 500. And we want to, in part 1, use the mean of 505. Okay. So here, let's be clear about what's our variable here. So it's the weight of a cereal box. So I'll go with weight again. W equals the weight of cereal box in grams. Okay. And so we know that W in part 1 is a normally distributed variable with a mean of 505 and a standard deviation of 5. So variance of 5 squared. And we want a proportion of boxes that will be underweight. So the probability that a cereal box weighs less than 500 grams. So again, interpreting the question accurately, yes, this would give us the same answer, but a box that weighs exactly 500 grams is not underweight. And so in terms of answering the question, we want the probability that W is less than 500. And we want that probability correct to 4 decimal places. Okay. So let's do that. Menu 552. Lower bound is negative infinity. Upper bound is 500. Mean is 505 in part 1. Standard deviation is 5. So it's 0.1587 to 4 decimal places. Part 2. Find the value of mu required to ensure that only 1% of boxes are underweight. Give your answer correct to the nearest gram. Okay, so what we're seeing here is 15% of the boxes are underweight if the mean is only 505. What does the mean need to be so that we only have 1% of boxes underweight? So again, sort of, does my answer make sense? I'm expecting the mean has to be more than 505. I'm going to redefine my variable. I don't need to redefine W equals the weight of a cereal box. That's still true. But now in this question, it's a normally distributed variable with an unknown mean. Okay. But we do know that the probability that the box is underweight needs to be only 1%, so 0.01. Okay, so we need to solve for the mean. So menu 3.1, menu 552 by normal CDF, negative infinity up to 500 with an unknown mean and a standard deviation of 5. Okay, again, it won't like that, but that's okay. We want that probability to be equal to 0.01, and we want to solve for m. And we do that, we find that the mean has to be, and it's a correct to the nearest gram, okay, so it has to be approximately 512 grams. So that makes sense. We expected it had to be more than 505, given that 15% or nearly 16% of boxes were underweight when the mean was only 505. Okay, part B, so therefore, this information is not relevant in part B. We go back to reading the original information. And my apologies, actually, it should really have, it should really have part A here. So this stem applies to everything. The amount of cereal in boxes. Okay, so as a check on the setting of the machine, a random sample of 5 boxes is chosen, and the setting is changed if more than one of these boxes is underweight. Find the probability, correct to 4 decimal places, that the setting is changed when the mean is 505. So we are going to use a mean of 505 here. So what's actually happened here now is what we're now dealing with is a binomial problem. So we're taking 5 boxes and we're interested in whether or not more than one of those boxes is underweight. Okay, so actually this is a binomial problem. Okay, so let's have B is going to be the number of boxes underweight. B is a binomial variable. We're choosing 5 boxes. The probability that any given box is underweight when the mean is 505 is this, 0.1587. So our normal probability becomes the probability of success in the binomial distribution. This is quite common as an example. Okay. So what do we want? Find the probability correct to 4 decimal places that the setting is changed. So the setting is changed if more than one of these boxes is underweight. So the probability that the number of boxes underweight is more than 1. Okay, that's what we want to work out. Now remembering that that's the same as the probability, it's a discrete distribution, so bigger than 1 is not the same as bigger than or equal to 1, it's the same as bigger than or equal to 2. So when we put our lower bound in our binomial CDF, it needs to be 2, not 1. Okay, so first things first though, I want to use that nice exact probability from here, so I don't want to use a rounded value, so I'm just going to go up here and I'm going to press Control C, so I've copied that value, so I can then put it in my binomial. So menu 55B for binomials, I press C. Menu 55B for our binomial CDF. Number of trials is 5. Probability of success, I'm going to paste my answer here, so Control V. Lower bound is 2. Up to infinity. So if we need more than 1, we need 2 or more, given that it's a discrete distribution. What did I type wrong? Oh, I typed 2 to infinity, sorry. So used to normal distribution. So the upper bound is not infinity. If you only got 5 boxes, we could have between 2 and 5 boxes underweight. So 2, 3, 4 or 5 boxes underweight. Okay, and probability correct to 4 decimal places again is 0.1809. Okay, so being precise about how you use that normal probability, copy and paste in your CAS, it's nice and easy, there's no excuse for creating rounding errors. Okay, example 4, I think this might be our final one. Yep. The weight distribution for packages of flour is normal. It is known that 3% of packages weigh less than 490 grams and 8% of packages weigh more than 570 grams. Find correct to 1 decimal place the mean and variance of the distribution. So A, be careful about that we want variance, not standard deviation. So we'll need to do just one little step at the end. Okay, so let's have again, W is going to be the weight of a packet of flour. And it is in grams. Okay. W is a normally distributed variable, but we don't know its mean and we don't know its standard deviation. Hence, we also don't know its variance. Okay, so this is one of those problems like we looked at in the previous video, where both mean and standard deviation are unknown, and we need to use standardization here. So we don't know the mean and we don't know the standard deviation, but we do know that 3% of packages weigh less than 490 grams. Okay, so 490 grams. we know that that's going to be 3%, and we know that 8% of packages weigh more than 570 grams. Okay, so this is where we're looking at W values. Now, because W has both an unknown mean and an unknown standard deviation, we instead want to rescale to the standard normal variable, which we know has a mean of 0 and a standard deviation of 1. Okay, so when we do that, the mean becomes 0. We know that to transform from the non-standard variable to the standard variable, we subtract the mean and we divide by the standard deviation. We subtract the mean and we divide by the standard deviation. Okay, so having standardized, we can now use inverse normal to find the probabilities. So we know from the original question that the probability that the weight of a packet is less than 490 is 0.03. When we standardize, that tells us that the probability that Z is less than 490 minus the mean divided by the standard deviation is 0.03. And so we can use inverse normal to find what this value should be. Okay. So menu 553. The area we know is 0.03. Standard normal, so mean is 0, standard deviation is 1. Sorry, there we go. So this value is approximately negative 1.8808. Okay. And then the other value, so I'm just going to move that over. And then the other value, so this one, from here we learn that the probability that the weights are bigger than 570 is 0.08. So that's the same as the probability of the weights being less than or equal to 570 as being 0.92 for the inverse normal probability. So that's the probability that Z is less than or equal to 570 minus the mean divided by the standard deviation. That has to be 0.92. So then we can use inverse normal to find what this value must be. So menu 553, area is 0.92, mean and standard deviation are correct, so it's approximately 1.4051, and then we can solve those equations simultaneously. So if we solve menu 371, we're going to have two equations. The variables are going to be mean and standard deviation. My first equation is 490, minus the mean divided by the standard deviation, and we know that that has to be equal to this first value up here, that one. And then my other equation, control divide 570 minus the mean and divided by the standard deviation, is equal to this value up here. Now remember, we have that pasting issue, so you can't just hit enter, it'll go into that first line of the simultaneous equations. So control C to copy it, and then control V to paste it down here. And then we find from this that the mean is approximately equal to, now what level of accuracy do we want? 1 decimal place. So the mean is approximately equal to 535.8 grams. And the standard deviation is approximately 24.347 grams. Now I haven't given that to 1 decimal place because we don't want the standard deviation, we want the variance. So I'm going to do 24 point, I'm going to write as many decimal places as I can see here, 34670805 squared to 1 decimal place, 592.8. Okay, now the units of the variance is not in grams, the units of the standard deviation is in grams, but the variance is in square grams, which is meaningless, so I wouldn't write units on the variance. Okay, so the work today and to finish the course is exercise 16D. After this you could be looking at the chapter 16 review exercise as some more revision of normal distribution. In particular, the extended response would give you more practice on these kind of worded problems.